Good day everyone, I am Vincent Manluloyo, one of the members of Group 6, and today we're going to report the results of laboratory activity number 5, which is about organic compounds with carbonyl group, aldehydes and ketones. We start off by knowing what a carbonyl group is. So the carbonyl group is a source of numerous important reactions in organic chemistry, mainly a result of the polarization of the carbon-oxygen pi bond due to the relatively high electronegativity of the oxygen atom. The simplest carbonyl groups are aldehydes and ketones usually attached to another carbon compound. Aldehydes and ketones are two closely related carbonyl-based functional groups that react in very similar ways. In a ketone, the carbon atom of a carbonyl is bonded to two other carbons. In an aldehyde, the carbonyl carbon is bonded on one side to a hydrogen and on the other side to a carbon. The exception to this definition is formaldehyde, in which the carbonyl carbon has bonds to two hydrogens.
Materials and methodology.
For the apparatuses, we use test tubes, pipettes, medicine droppers, 10 ml graduated cylinder, Bunsen burner, water bath, wire gauze, 250 ml beaker, test tube holder, and test tube rack.
And for the materials, we have formaldehyde, benzaldehyde, acetone, Tollens reagent, Skiff's reagent, Fillings reagent, and 2,4-dinitrophenylhydrazine. We also use potassium permanganate, diluted sulfuric acid solution, 10% sodium hydroxide, iodine solution, and water. And this is the illustration of the experiment, and it shows how it has been done. Testing of properties. So in a 2,4-dinitrophenylhydrazine test, we place 3 to 5 drops of formaldehyde, benzaldehyde, and acetone in 3 separate test tubes. And then we add 3 to 5 drops of 2,4-dinitrophenylhydrazine to each tube.
I have two test tubes on the screen, which I have labeled A for aldehyde and K for the ketone. Just as a comparison, I've also got the Benedicts, which I prepared earlier. First of all, we add some aldehyde. You can see that the aldehyde has reacted as soon as it's been added to the Tollens reagent. You can see that lovely kind of grey-black precipitate which is forming straight away. And with the Benedict solution, you can see that there is no reaction yet. So that's the aldehyde. Next up, we got the acetone. Remember, that's also called propanone. And add that to the Tollens reagent, and you can see there's no obvious reaction happening, even if we add a little bit more.
Next is Tollens test. Again, we place 3 to 5 drops of formaldehyde, benzaldehyde, and acetone in 3 separate test tubes and add 3 to 5 drops of freshly prepared Tollens reagent to each test tube. After that, we shake and warm it gently in a water bath in 3 minutes.
The first thing I'm going to do is I'm going to make the Tollens reagent using silver nitrate, sodium hydroxide, then ammonium hydroxide. I'm going to take that solution once I make it following the directions. I'm going to disperse it into 5 test tubes equally. And to the first test tube, I'm going to add benzaldehyde, second acetone, third 3-pentanone, fourth formalin, and the last one acetaldehyde. Now remember, on a Tollens reagent, we're talking about it being an oxidation reaction. And we do know that aldehydes undergo oxidation in this reaction, and ketones do not. To make this easier to see, I actually doubled the recipe, and right now I have in here silver nitrate and my sodium hydroxide. I'm going to go ahead and mix this. So I'm going to go ahead and mix this. We have a dark precipitate going on in here. And then the directions say add just enough ammonium hydroxide till the precipitate goes away. So I'm going to add a couple of drops. Let's mix that, see if it goes away. Not yet. Put in a couple more drops. About 5 drops there, I'd say. Ooh. We've got a lot of the precipitate. Notice how it's going to the bottom, and then it's much more clear at the top. I'm going to go ahead and add about 5 more drops, because I don't want to put too much in there. And then I'm going to actually transfer by decanting. I'm going to transfer just the liquid. So I'm going to allow the solid to settle to the bottom, and then I'm going to use a transfer pipette, and I'm going to go ahead and put it in this so I have a little easier time to go ahead and put it in my test tubes. All right, I'm going to go ahead and transfer just the liquid, not the precipitate that remained on the bottom. And this is called decanting because I let the solid settle to the bottom and I'm only removing the liquid from the top. All right, now I'm going to go ahead, and it looks like I have almost 10 mils. So I'm going to put about 1 mil into each one of these. In fact, I'm using the transfer pipette I'm using actually has a milliliter mark on it. It makes this a little easier for me to go ahead and measure. And it looks like we did good. All right, I'm going to go ahead and add a few more drops than the directions said. The directions say to add 2 to 3, but I have notes 4, 5, 6, 7 to add about 7 drops. So I added my benzaldehyde to the first one. It has a beautiful aromatic odor, as we know benzaldehyde should. So I'm going to go ahead and mix that and then let that set. I'm going to go ahead and add acetone, 3-pentanone, formalin, and acetaldehyde, and then they need to rest a bit, and we'll see what happens with our results. So I'm going to go ahead and let these set for a little bit so they can go ahead and process. But right off the bat, I saw a big difference on formalin, which is a form of formaldehyde. Immediately when I put in the drops, it turned this dark color, and the same thing with acetaldehyde. These other 3, we're going to see what happens. All right, it's been about 10 minutes. I know it's kind of hard to see it, but there's actually a bit of a silverness to the last 2 here. So the formalin and acetaldehyde did get a silver mirror. I know we have the gray in there, so it's a little hard to tell, but I'm letting you know it did have it. The other 3, this one is benzaldehyde. It should have reacted. It should have made a silver mirror because it is an aldehyde. Now these other 2 aren't aldehydes, so they shouldn't react. And let's take a look. So neither one of them reacted.
Next is Fehling test. Same procedure, but instead of freshly prepared Tollens reagent, we add 1.0 ml of Fehling solution to each tube and shake and warm it gently in a water bath in 3 minutes. Next is Gibbs test. So we place again 3 to 5 drops of formaldehyde, benzaldehyde, and acetone and 3 separate test tube and add 2.0 ml of Gibbs reagent to each tube.
So this is what our lab setup looks like. We're going to add about 1.5 milliliters of Schiff reagent to each of these 5 test tubes. Notice how the Schiff reagent is colorless. So what we're looking for is a bright, bold purple color that will indicate a positive test, which shows us that we have aldehyde. So we first are testing out water, which is our negative control. We know water doesn't contain the aldehyde functional group. We'll test out acetaldehyde or ethanal, benzaldehyde, propanone or acetone, and cyclohexanone. We'll give each one just a little shake so you can make some observations. We're looking for that dark purple or magenta color to indicate a positive test.
So in the oxidation, we mix potassium permanganate solution and diluted sulfuric acid solution in 3 test tubes and added 0.5 ml of formaldehyde to the first tube, 0.5 ml of benzaldehyde to the second tube, and 0.5 ml of acetone to the third tube.
The oxidation of the aldehydes and ketones using the permanganate solution. We'll get again 3 test tubes. So this is now the test tubes containing the potassium permanganate and the sulfuric acid dilute to test for the oxidation reaction of the aldehydes and ketones. So to the first test tube, we are going to add the aldehyde. I want you to observe what happens. To the second test tube, let us add the benzaldehyde. And to the third test tube, let us add the acetone.
Lastly, a iodoform test. So in a 1 ml of acetone, we add 1.5 ml of 10% sodium hydroxide solution and 0.5 ml of water. So here we repeat the procedure, but then we use benzaldehyde and formaldehyde instead of acetone.
Moving on to the results and discussions of the experiment. First was to observe and record the physical properties of formaldehyde, benzaldehyde, and acetone for its color, odor, flammability, volatility, solubility in water, and solubility in alcohol. Now, I want you to observe the table. First is formaldehyde. Formaldehyde is a colorless gas. It has a pungent and suffocating odor which is like a strong pickle-like odor that is commonly used in many manufacturing processes. Formaldehyde is flammable gas or combustible solution and is very volatile in high ambient temperatures or humidity and liable to accumulate indoors in high concentrations. Formaldehyde is readily soluble in water with solubility greater than 100 grams or 100 ml, which is 20 degrees Celsius. Formaldehyde is also soluble in alcohol with solubility greater than 100 grams or 100 ml. Moving on to benzaldehyde. Benzaldehyde is a colorless liquid and it has an almond oil odor. It is combustible and is volatile as you can observe in the table. It has 6.95 grams per liter or 25 degrees Celsius, which is slightly soluble in water. It is also completely soluble in ethanol. Next is acetone. Acetone is a clear, colorless liquid and it has a pleasant, fruity odor. It is also flammable and highly volatile. It is soluble in all proportions of water and is soluble in ethanol, which is alcohol. Next is the testing of properties of 2,4-dinitrophenylhydrazine test, which is also known as Brady's reagent. Aldehydes and ketones react with 2,4-dinitrophenylhydrazine reagent to form yellow, orange, or reddish-orange precipitates, whereas alcohols do not react. Formation of a precipitate therefore indicates the presence of an aldehyde or ketone. The precipitate from this test also serves as a solid derivative. A successful test is indicated by the formation of a precipitate yellow, orange, or red known as the nitrophenylhydrazone. The reaction is condensation reaction, or water is eliminated. The product is named using the name of the aldehyde or ketone followed by 2,4-dinitrophenylhydrazone, for example, ethanol 2,4-dinitrophenylhydrazone. 2,4-dinitrophenylhydrazine can be used as a method for identifying aldehydes and ketones. The 2,4-dinitrophenylhydrazone formed is a solid that can be purified and its melting point determined. Comparison of the melting point with the table of known values could be identify the aldehyde or ketone. The 2,4-dinitrophenylhydrazone derivatives are all orange-yellow solid. Both aldehyde or formaldehyde and benzaldehyde and ketones, which is acetone, gives positive results, which indicates by a yellow precipitates, which means that the solution are all aliphatic compounds. In short, formaldehyde, or known as methanol, gave off yellow precipitate. The benzaldehyde also gave yellow precipitate. And lastly, the acetone, also known as propanone, yellow crystalline precipitate. The picture on the right shows the chemical equation and the results of the experiment, which is yellow, red, and orange.
Alright, next is the Tollens test. This test is also called the silver mirror test. Tollens reagent consists of silver ammonia complex in ammonia solution. Aldehydes reacts with Tollens reagent, gives a gray-black precipitate or a silver mirror. Always a freshly prepared Tollens reagent should be used. Aldehydes are oxidized to the corresponding acid and silver in Tollens reagent is reduced from positive 1 oxidation state to its elemental form. Generally, ketones do not respond to this test. For the results of formaldehyde or the methanol, silver-like precipitates, and benzaldehyde also gives silver-like precipitates, and acetone or the propanone, no changes or reaction. Okay, next is the fillings test. Formaldehyde or the methanol, reaction of formaldehyde, also known as methanol, with filling solution. This solution is initially made as two separate solutions, fillings A and fillings B. Fillings A is a blue aqueous solution of copper sulfate, while fillings B is a clear solution containing aqueous potassium sodium tartrate and sodium hydroxide. On mixing equal volumes of these two solutions, a final deep blue colored filling solution is obtained. The filling solution is used to differentiate between ketone functional groups, water-soluble aldehydes, and as a test for monosaccharides. Methanol, on reacting with filling solution, produce sodium methanate, cuprous oxide, and water, and the color of the solution changed from blue to red. So as you can see this picture, the methanol added to filling solution, which is the A and B or the blue color, added to NaOH yields to calcium carbonate, HCOONA or the sodium methanoate, added to Cu2O or the cuprous oxide or the red PPTS, added to 3H2O or the water. On the other hand, benzaldehyde and acetone, filling solution did not react to both acetone and benzaldehyde. Benzaldehyde does not contain alpha hydrogen, so intermediate enolate formation did not take place. Thus, it it did not react with filling solution. Ketone did not react with the filling solution unless they are alpha hydroxy ketones. Acetone is not alpha hydroxy ketone, so it will also not reduce the filling solution.
Next is the chef's test. So formaldehyde or the methanol and the benzaldehyde reacts with the chef's reagent. Whenever an aldehyde with alpha hydrogen is added to the chef's reagent, it will turn from colorless to magenta color. So these formaldehyde and benzaldehyde give all the normal test of the aldehyde group. Thus, both reactions gave a pink or magenta colored solution when reacted with the chef reagent. On the other hand, for the acetone, it does not give any reaction with the chef's reagent because acetone is a ketone and ketones do not react with this kind of reagent. And moreover, one type of a chef reagent is the rosanoline hydrochloride solution, which decolorize with sulfurous acid. So next we have the oxidation. Aldehydes can be quickly oxidized to generate carboxylic acid because aldehydes have a proton connected to the carbonyl carbon. On the other hand, because of the lack of hydrogen, ketones are generally inert to these oxidation conditions. However, ketones can still be oxidized but under high conditions. So there are a wide variety of reagents which can cause the oxidation of aldehydes to carboxylic acids. And the most common reagent for this conversion is the CrO3 or the chromium trioxide. It is an aqueous acid, also called Jones reagent. This reaction generally gives good yields at room temperature. So we have here an example. So we have here our aldehyde, which is the hexanol, treated or reacts with CrO3 and H3O or the hydronium, will yield to a carboxylic product which is the hexanoic acid. So, mao ni siya. And as what I've said before, because ketones do not have hydrogen atoms attached to their carbonyl, they are resistant to the oxidation, and only very strong oxidizing agents such as potassium manganate or the potassium permanganate solution oxidizes ketones. However, this type of powerful oxidation occurs with cleavage, breaking carbon-carbon bonds and forming two carboxylic acids, and because of its destructive nature, this reaction is rarely used. So we have here an example of the reaction. So we have the cyclopentanone here, our ketone, reacts with the KMNO4 or the potassium permanganate, yields with a product of two carboxylic acids, which is the pentane dioic acid. Now let's proceed to the iodoform test. So a solution of iodine and iodide in NaOH or the sodium hydroxide can be used to test for methyl ketones or secondary alcohols adjacent to a methyl group. When iodine and sodium hydroxide are added to a compound that contains either a methyl ketone or a secondary alcohol with a methyl group in the alpha position, a pale yellow precipitate of iodoform or triiodide methane is formed. This iodoform test will help identify the presence of methyl ketone on the compounds of aldehydes and ketones. So we have here an example, the reaction of the secondary alcohol or the methyl ketone with the iodoform reagent. So it will result to the formation of the yellow precipitate iodoform. Moreover, we have here pictures. So this picture shows the different reactions of the compounds on the iodoform. So first, for the test tube D, which contains formaldehyde, it did not change to light brown color, which indicates that it has no presence of methyl group that is directly attached to a carbonyl. On the other hand, both test tube B, which contains benzaldehyde, and test tube C, which is the cyclohexanone, change its colors to light yellow, which means that the two compounds are positive for the iodoform test. Moreover, acetone from the test tube A also changed its appearance, but not to light brown. Instead, it changed from clear to translucent appearance. So the test tube B and C were then combined with sodium hydroxide to turn them back from colorless compounds. So a positive result is a cloudy yellow solution or a yellow precipitate, and a negative result of a uniform test is a clear yellow or orange solution with no precipitate. If the sample is not water soluble, a small organic layer separate from the solution may be seen. It will likely on the top. This layer may become dark yellow or brown from dissolving the iodine. Vigorously mix the tube to encourage a reaction, but if the darkened organic layer remains and no precipitate forms, this is still a negative result.
Now let's head directly to the guide questions. For the first guide questions, it is which reaction or test will distinguish between ketones and aldehydes? The second is how are aldehydes and ketones used in the medical field and in the industry? For the first question, so Tollens test, also known as a silver mirror test, is a qualitative laboratory test, and this is the most commonly used when distinguishing between an aldehyde and a ketone. Aldehydes can be oxidized into a carboxylic acid while ketones cannot. Tollens reagent and a silver nitrate and ammonia mixture oxidizes the aldehyde to a carboxylic acid. The silver ion silver is considered to be pure silver. Ag is S, which means the silver is solid, and the solid silver forms a silver mirror-like film on the inner wall of the test tube. Ketones do not react with Dolan's reagent and thus do not cause the formation of a silver mirror on the test tube walls. For the second question, aldehydes are versatile compounds that can be used to make resins, dyes, organic acids, perfumes, detergents, and soaps. Formaldehyde is the most widely produced aldehyde on a large scale. Formaldehyde is well known for its preservative and antibacterial properties, and formaldehyde-based chemistry is used in a variety of products including composite and engineered wood products used in the building and construction. Cinnamaldehyde has been used to treat illnesses such as common cold. Moreover, according to research, it is used as a natural medicinal compound to treat the common cold and diarrhea. Cinnamaldehyde also aids in the treatment and prevention of cancer. In addition, when diluted to 10%, aldehyde formalin can be used as a treatment for oven foot root. Now we are actually done with aldehydes. Let's go to ketones. In medicine, ketones are used in chemical peeling and for acne treatments. Furthermore, a ketones in blood test determines the concentration of ketone bodies in your blood. Ketones are substances produced by your body when your cells do not receive enough glucose or blood sugar is the primary source of energy in your body, and ketones can be detected in the blood or urine. High ketone levels may indicate diabetic ketoacidosis or DKA, a diabetic complication that can result in a coma or even death. Acetone is the most commonly used ketone in the industry because it is an excellent solvent for a variety of plastics and synthetic fibers. It is commonly used in the home as a nail paint remover and paint thinner. The MEK or the methyl ethyl ketone, also known as butanol, is a common solvent and it is used in the manufacture of textiles, varnishes, plastics, paint remover, paraffin wax, and other products. Now, in conclusion, to summarize this experiment, aldehydes and ketones react with 2,4-dinitrophenyl hydrazine reagent to form yellow, orange, or reddish-orange precipitates, just like what we saw earlier in the experiments. Whereas alcohols do not react, aldehydes reacts with Tollens reagent, gives a gray-black precipitate or a silver mirror on the silver mirror test, and for the filling solution did not react to both acetone and benzaldehyde. Whenever an aldehyde with alpha hydrogen is added to the Schiff's reagent, it will turn from colorless to magenta color. Ketones do not react with Schiff's reagent, thus acetone, which is a ketone, did not give any reaction with Schiff's reagent. Aldehydes have a proton connected to the carbonyl carbon, and they can be quickly oxidized to generate carboxylic acids, and ketones do not have a hydrogen atom attached to their carbonyl, so they are resistant to oxidation. For the iodoform test, it helps identify the presence of a methyl ketone on the compounds. Aldehydes and ketones, while the tolerance reagent is the most commonly used when distinguishing between an aldehyde and a ketone. So basically that's it, and these are the references that we have utilized in order for us to identify the answers to these questions. And for the experiment, there are also YouTube links that are given in the references. So thank you for listening, and we are group 6, and we're out.